problem that we're looking at is to try to come up with the area underneath this curve. This represents our transition to the other area of calculus, what's called integral calculus, and that will occupy you through the remainder of this semester and the bulk of next semester. And, so this is sort of day one of that. I want to look at a different figure because the software I've got I didn't write a special program for it. This is a program called WinStats that was created by mathematician and math teacher. He taught at Phillips Exeter in New Hampshire. The problem I want to put out here is related to the one you've been working on. It's the problem of trying to approximate this area of the circle. And so I gave a curve where we actually know a formula. In this circle, the radius is 1 unit, and so the length of a side of the square is 2 units. And the technique that I want to illustrate is something called Monte Carlo integration. It's finding areas by using random processes. So what this simulator does is it shoots a dart. When I do one trial, it just creates a random dot. And it marks down up at the very top, you can barely see it, it says 1 equals success. So what it's doing is it's essentially taking a random number generator and generating an x and y coordinate. And then it records whether the point that it generates lands inside the yellow circle or outside. The random numbers are restricted so that you always get coordinates within the rectangle or within the square. What's the area of the square? 4. Okay, so if we pop back over here and make a couple of notes, what we have is that the square area is 4. And so if here's the plan. Shoot a lot of random darts and determine the proportion R landing in the circle. And then if we multiply R times the square area, so that's R times 4, to get the circle area. Okay, because if you count what fraction of a bunch of randomly thrown darts lands inside the circle, well, that circle is a certain fraction of the total area of 4. And so I've got the circle area divided by the square area is approximately equal to this ratio that we're going to estimate. Random number generators, a good one, generates numbers that have properties that make them approximately like true random numbers. So you're not actually seeing coordinates here, and doing this one at a time would get really, really tiresome. So far we've got 3 successes in a row, 4 in a row, 5 in a row, 6 in a row, 7 in a row. Well, that doesn't make for much of a surprise because an awful lot of, oh, there's one that's a failure. That yellow circle is a huge proportion of the area of the entire square. But what's more fun is to actually do 1,000 in a row. It looks like that. And now we've got 1,000 randomly distributed points on there, and if you go through and count, what it tells me is that the percentage out of 1,000 that were success is 0.7660. We could do it again. We could do another 1,000, and we get, wow, about the same thing. We could do another 1,000, we get 0.7770. So if we do another 1,000, I'm just trying to get a sense of how much variability is in this, we get 0.8060. So 806 out of 1,000 random darts fell inside the circle. It's not so much fun to only do that many. If we can do 1,000, why not do 10,000 or 100,000? So here's 100,000 random darts being thrown at the same target.
Well, that's a lot of darts, right? So what you find is that this one comes out 0.7829. And if I do another 100,000 darts, I get 0.7875. And I think what you'll observe if we do this several times is that the first two digits are never going to change. That's what's called the law of large numbers, that when you have a process that's repeated a very large number of times, you get a much decreased variability in the estimators that you get out, the numerical values. So what would we expect this to be? Well, if we took the circle area and divided it by 4, that's about what we're finding. What is the area of a circle in radius 1? Now this is actually equal to pi times 1 squared over 4, which is pi over 4. And what's a good decimal approximation for pi over 4?
6, 7.
Yeah, your little calculator right there will tell you 11 decimal places, right?
785.
785. Okay, so what you see is that with 100,000 darts, we're pretty much nailing down the first 2 decimal places. That requires a lot of darts, right? You'd never throw 100,000, but that's where it takes just to estimate this area. So this is not a terribly efficient process for estimating areas. So of all the methods that you would have thought of to approximate this area, this is probably not one that you would have come up with. The idea of, well, we've got a rectangle here, right? It goes up to 1, and from -1 to 1. So the total area in this picture is actually 2. So we do know right off the bat that the correct answer for this area can't be any larger than 2, because we can embed the whole picture inside a rectangle of height 1 and width 2.